Hello,
Hello.
everybody. It hasn't
Yes.
started yet. You're in the past, YouTube. We're talking in the future. Oh, no, it auto started. Oh, my goodness. No, I
Amazing.
don't believe it worked that easy, that quick. I
Wonders
changed the
whether it's
setting
just
for auto start, so who knew, right? So, how you doing today, my friend?
doing good. Doing good. It's been a really busy week and I haven't had as much time as I would have hoped to to get onto the whole JTAG thing like we discussed last week. Uh, and oh, before we get too much further, just some news, practical housekeeping. Next week I will be away. Uh, and won't be able to stream on Friday. So um, maybe, hopefully, you can carry on without me, or have another guest in my place would be cool. But I just wanted to tell everyone that I won't be here next week. But look forward to catching up with everyone again the week after. I'll probably mention that briefly at the end too. So I've been just reading up more. I think I've come to the conclusion. So last week I was showing some of my FPGA and ESP32 board I'm working on, and the question came up about the serial interfaces between all the chips. So we all use things like I2C, or it's often called two-wire bus in data sheets because I2C, I2C is a
Yeah,
trademark owned by
right.
Philips, which was then NXP, which is now Freescale. Um, So you have to actually read the whole data sheet and look at the protocol and realize, oh, that start condition and end condition and 7 address bits and 1 acknowledge bit, that's I2C.
Right, right.
But we didn't quite get to carry on our discussion about serial protocols. So you're showing us something there. Um, we'll come back to the whole JTAG thing. I have made some decisions about that, by the way, but we'll talk about that later.
Okay.
So what
So,
are you showing us there on the scope, Bill?
I
That's a
just happen
beautiful.
to have, yeah, I just happen to have thrown my MDO scope, my Tektronix. What kind of scope is this? I keep forgetting these days. It's an MDO 3104, and it has a built-in I squared C analyzer, and then protocol analyzer, and then my scope came with a demo circuit. And so I'm just running a simple demo circuit where it's spitting out I squared C and it's throwing errors. You'll see errors every now and red. But what
And
you're
the errors
seeing,
are there intentionally, right, by the demo
right,
circuit, is
that's right,
yeah,
that's right.
yeah.
So it's like if you start the whole conversation and you don't finish it, it'll throw an error. So, and what's interesting about I2C, I don't see any glitches on here, but in real life, I2C is a shared bus. It's open drain, like open collector, which means devices can pull down, but they don't pull up. A pull up pulls up, and you adjust that resistor, that pull up, for how fast you want it to pull up, quite honestly. So when we get to things like if we were to go into this, and honestly, read the Wikipedia page, it'll give you a good demonstration I squared C. But we start by bringing the clock low and then the data line low, or is that the other way? We bring the data line low and then the clock line low, and we give it an address. And right after that, the bus turns around. It does an ACK. So we go bit, 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 your turn, bit, bit, bit. And that first ACK is kind of where it says, yes, I heard you on here, I'm at this address. So it's important to understand that for I squared C, or three-wire, two-wire interfaces, that you have to have that address somewhere. On SPI, we do it with an external select. We have a select for you and a select for you. But
Yep.
on I squared C, you've got to either have it programmed into the manufacturer for that chip, or more likely you have several addresses and you pick which one that chip will respond to. And
Yeah.
we can
And
see those coming
so
up on the display.
right. So just looking at the Wolfson uh, audio codecs I'm designing into my board, they use an equivalent. They use I2C, or two wire is one option, SPI is another. But the address, they have two external address pins so that the idea is some manufacturers don't give you that with the chip. If it's a 6-pin TSOP version of the package, they leave off the address pins, and you're stuck with the default address factory programmed. And
how would you use 2 of them then?
Well, that's it. You can't use 2 of the same chip if you're doing that. You may be able to use other chips from other manufacturers because they'll have a different factory programmed address. The other interesting thing, so I2C is actually super clever, even though it's kind of slow. What's the fastest? I think the full
400K is the standard.
400 kilobits a second, so it's not super fast. It's just barely fast enough to get a reasonable sampling rate on an 8-bit A to D or D to A converter on the bus.
Right.
So it's used for a lot of those sorts of things. But
and it can go faster.
So do you have a notepad there? I'm just wondering, or maybe I could do it here. We should talk about Open Drain. You mentioned what.
I wanted to have you draw Open Drain, and we didn't get a chance to talk about it before the show. Can you do that? Because you do a great notepad. I gotta improve my notepad chops.
Let's just try it. So I'm gonna. Where's Skype share screen here? Here it is, share screen, and I'm gonna share this one.
Alrighty.
So I don't know if you can. We're gonna get the infinite video echo of doom here for a second.
All right, so we're going to add streams, NDI. Hey, there you are. That's always amazing. Except it didn't work.
Okay, so I'm going back to Skype to do share screen.
And stop and start it again if you would.
Yep. I've got to pick what's the right monitor? Desktop. This one. No? There it is. So
whoops.
Now I can
there's your notepad. Yep. Got it.
Yeah. So let's just do this real quick. I'll get my pen out. Hopefully this works. Maybe not.
Mondo 8-bit just said hi. Everybody's saying hi. Hi, Mike. Hi, Dave. Hi, Unix. That's the Unix operating system is a member of us.
Yeah, I don't know what my pen's not working right now. It's linking to the wrong monitor.
I hate technology. You know, for all the stuff technology gives and it takes away.
Well, I can do this. Let me share the other monitor and use the pen on this one. That'll work. I'll fix it later.
All right. So we've got the Infinite Tunnel of Doom here with the great commercial for Tektronix.
So now we're looking at Notepad again. Okay, and let's go. Okay, that appears to be functioning. So, yeah, let's go. Pick size. I want a thick line. Okay, so Open Drain looks like this. You have inside your chip, you've got a pin. That's your, let's say you've got SCL, which is your clock line. Oh, that's terrible. And oh my gosh, it's hard doing this when it's on a different monitor, I tell you. And
yeah.
SDA, so serial data. And this has an external pull-up to VCC. So inside, what it means is the output is just the drain of an N-channel MOSFET. And that goes to ground. So what does this do? It means that the bus is here. And this resistor is usually 2K. If you want to go 400 kilobits a second, you need uh, maximum 2K. Otherwise, you get the rise times
Slew rate's
become
too slow.
So
Yes.
if you look at your scope there, you can actually see that all the falling edges are very sharp and square, and the rising edges are exhibiting that RC kind of,
Right.
That curve, which is okay. It still has a fast enough rise time. But a lot of problems on actual designs when you're prototyping, and if you have a lot of things on the bus or a long line, you don't have a strong enough pull-up. The pull-up in the earlier versions of I2C was a 4K7 resistor.
Right.
And it had a slower rise time. And the more trace routing you have, the more capacitance you have on the line, and the more chips you have in the bus, the more capacitance for inputs, because there's inputs connected to this as well as outputs.
Right. And
So
that
the
RC
gate
curve is
capacitance-
important to recognize. If when you see
Yeah.
that exponential curve after doing this for years, electronics, you go, that's a soft pull up and a hard pull down.
Yeah. So what it means is basically, it gives us a couple of advantages. We can just have two wires that go to all the chips on the bus, and there's no contention. If you send out a data packet, so Bill, I wonder if you could actually zoom into a start frame.
Yeah, let me see if I can redo this now, because I screwed up all the settings.
Yeah, like
You
that
keep
first
talking.
one, that's the yellow. It's got the start condition and then the address and an acknowledge.
Right.
So right there, yeah. What you're zoomed into there is the start condition. So the blue is your data line. It goes low. It pulls down first to say this master device. So what am I getting at? It means two things. You can have multiple slaves and multiple masters on the bus, because any device can initiate a start condition by pulling its data line low before the clock line goes low. And then the clock goes low, and that's a start. That means I'm starting to transmit. And then there's a 7-bit address comes out. But what it means is if two devices try to initiate a transfer at the same time.
Right. Go on.
If two devices initiate a transfer at the same time, the address gets corrupted. And so you either get no acknowledgement, so none of the devices on the bus, because it'll be the wrong address, right? So
how often is
devices
there multi-master, though? A lot of times you have a single master in a series, and they're changing those words, master and slave, aren't they? They've become like not words we want to use in reference to electronics.
I don't know about that. Yeah, I guess in the current political climate,
Yep.
people are overly sensitive
But
about these things. But it's just a bus with chips.
It's just
not
a bus, yeah.
So anyway, but yeah, you could. But it's a multi-master bus, basically. Like any
Right.
device can. Well, call it a freedom of speech bus. There you go.
Yeah.
Any device can initiate communication, and if they both try it at the same time, they're both pulling bits low because they're both trying to send to a different address. And so the data line will be pulled low by both of them at different times, and the address bits will become corrupted. So naturally at the end of that, they can detect that. They can detect
Collision detection, yeah.
Each device can easily detect if another one's trying to transmit at the same time, because what it measures out of the SDA pin doesn't anymore match what it's trying to assert on the SDA pin. And that difference is very easy to flag with a comparator inside the chip. So it can just say there's a
Right.
collision, and they both
Right.
stop. They both stop and release the bus, and then wait
And
some-
back off for a random period of time or something.
Yeah, and then try again. So
That's how
It's
Ethernet worked on coax in the old days.
Yeah, and then we went to collision. Yeah, CSMA.
CSMDA or whatever it's called, collision. Yeah,
Yeah. Ethernet started with a carrier, like the clock would begin, so that would give PLL chips, the Ethernet PHY would give it enough clock cycles up front to sync the PLL, and then when the start of frame happened, it could easily use the clock in the Manchester encoded signal, or 8B10B, whatever it is, one of those,
right.
to bring it into the shift register for the input. So
Right. Carrier sense multiple access is what I was trying to think of.
Yeah, CSMA CD with collision detection.
Right, with collision detection. That's right.
So we have the same thing, but on a miniature scale at 3.3 or 5 volts, depending on what you're doing there.
Right.
But you're right. In most situations, you have one microcontroller, and that kind of, you treat that as the owner of the bus, and then you have all the other peripheral chips hanging off of it.
Right.
So I2C is pretty elegant, but you've got to watch those pull-ups, because it's a trade-off of wasting power with more resistance on the line,
Right.
or I mean to say with more DC current, because you have low value pull-ups. But sometimes a lot of problems are solved on I2C just by changing the pull-up resistor values.
Right. Right. And you can see we almost see some glitches in here, like right here. I can see the formation, and it's right when this time period ends. And if you have a real strong pull-up, you tend to get stronger glitches. So the act of going faster also means the moment everything jumps off the bus, it starts going up.
So why is that, Bill? I have my own hypothesis, but...
Well, it's like you're not low, I'm not low, and the pull-up starts taking, then the guy goes, wait a minute, it's my turn, and he goes low again. So it's just a moment when everybody's off the bus. It's kind of I think of it as a moment of relaxation, right? So
yeah.
and your strength of your RC will come through then.
So to me that looks like crosstalk, but it may not be crosstalk from the actual signal traces. It's unlikely to be, in fact, because you've got separate shielded scope probes going.
That's right.
So to me, what looks like crosstalk, this is a good discussion point actually. That looks like crosstalk when the clock signal goes low, right where your mouse cursor was there for a second. Your clock signal goes low hard, but there's a downward glitch on the data line.
Right, and it may even be some crosstalk. I didn't design the Tektronix board, but that's where I'm used to seeing them, is right at the end of what I think of as cell times. I think of this as a cell, basically a clocked time.
Yeah.
And the fact it coincides could be crosstalk, but Mike Fikes has seen this where he saw real strong positive glitches, and he asked me if that was normal, but what I couldn't tell by looking at his picture was what his scope was set for a scan time. And once I realized he was going real slow, it was obvious it was just the RC letting go from time to time.
My hypothesis of what that is that it's not crosstalk through traces, but it's actually power supply rejection. Because you have strong pull-ups, you're dumping, when you pull that line low, you're dumping the capacitance of the bus.
Right.
You're basically short-circuiting it through an N-channel MOSFET on the driving gate. So it's taking all that capacitance and just shorting it to ground when it's pulling low. So a lot of current flows at that moment, and that's going to cause a dip in the overall I2C bus power supply line that feeds the two pull-up resistors. But I don't know. I'd have to do some. That's just a
We'd
hypothesis.
have to look more to determine. Yeah.
And
the fact I don't
that heavy current, flowing at that moment of pull down, and you don't see it when clock line is already low, it's still clamped through the pull-up, and then the data line goes low, but we don't see that in the other one because it's already been clamped low. So the other thing that's easy to forget, I've done FPGA cores to interpret I2C. I did an update to an I2C peripheral device years ago. And one of the things that was really hard to remember in architecting an I2C peripheral in VHDL is that if it's true I2C, your clock is a pulse that's fully contained within one data bit period. So what you'll see there is you get a start condition. So what you have to do is build a state machine that reads every data bit period, whereas it's awfully tempting just to make a shift register that samples the data bit on the rising edge of the clock. But the rising edge of the clock may not be very good because of that RC pull-up curve. You might want to sample on the falling edge. And for that reason, the people who invented I2C had the wisdom to say a clock has to be a full rise, top, and fall within the time of a data bit. So you could actually, even if you wanted to, you could sample it on the trailing edge of the clock pulse instead of the leading edge of the clock pulse and get a much better,
It's time to park a truck in there. Let's say that, since we're using both edges, you have time to parallel park and still meet your clock setup and hold times and stuff.
So it's slow, but it's elegant. So this is why it's so popular and why so many small peripheral devices that hang off microcontrollers could use it. So you're contrasting SPI because that's the other favorite amongst. So by the way, I2C stands for Integrated Circuit Bus.
Ah, right.
SPI stands for Serial Peripheral Interface, if I'm not wrong, Bill. So
sounds
the difference
right.
there is you need more wires.
Right, yeah, and that's what this drawing, this is actually from my Hackaday article on the two of them. And SPI is simpler because it's not a shared bus. It could go faster without some of the overhead, but it has the overhead that you have to have discrete chip selects. Now, that means that you can have multiple chips of the same manufacturer all gang together, obviously,
So that's particularly useful if you want lots of flash memory, for example.
Right.
And also being an active driven bus with tri-statable. So clock. So SPI also is not multi-master from what I understand. It can't be because the clock must be driven from a master, right?
That's right. Yep.
So that's one.
But the master can do a read cycle. Obviously, it can say, "Hey, you." It's just it has to initiate the conversation, say, "What do you have to tell me?" And the guy then. So there is this other data bus right here. So there is an input and an output, Mossy Missy, and this is part of what actually Mike just posted a link to the Hackaday article about the naming conventions for these. And that's the other thing with SPI is not only do you have these separate chip selects, but you've got an output from the master and an input to the master instead of sharing the same data bus like I2C does.
Yeah, and so you don't have addressing embedded in the serial interface like I2C either. So the very first thing you do to initiate I2C communication is you say address, and you get either the device that has that address either pulls the acknowledged low to say yes, I'm here, or there's no device by that address and nobody pulls it low, and like I'm trying to hit the wrong. Sending a message in a bottle, but there ain't no one at the other end. SPI is just hard chip select, so you have to do all your addressing with extra pins on your on
which
your
can
device.
be I/O ports. The good news is the actual SPI high-speed shift register mechanism and the chip selects can be different things. You can manually pull an I/O line low and say, I've just selected device 4 and kick it out your SPI bus depending on how you've constructed your SPI bus.
Right, or if you need if you got limited
More
pins,
than
you do some decoding with a 138 or something.
right. It's 74LS1383 to 8 decoder is a great example.
Yep, or a
Or dual
154 if you want 16.
LS139 dual fours. Yeah.
Yeah. One of the things I really liked too about SPI is it's so, because it's synchronous and simplistically master slave. You don't, like, for some devices they don't even have a return data line. You can just
Don't need it sometimes. Yeah.
You can just go down if you only have one device that's always in use. You can pull its chip select low, and all you need then is 2 wires, like I2C.
That's right.
But it's super simple and fast because you send a clock, you send data, and then also because it's an actively driven bus and not a pull-up multi-drop, that means it goes a lot faster. So, and I don't think there's any specification that gives a hard limit to the speed. It's really more up to the individual devices you're using and what the manufacturers say they can possibly do, and then the signal integrity on the board. Because I've seen designs where they were driving SPI at, tens of megahertz clock speeds, and it worked flawlessly because the board was laid out well and had good ground reference planes. And so what's your favorite out of these, though? I guess they have different.
Well, we used to manually make SPI buses in the old days. We'd grab like LS, I want to say 164, 165, one of those, parallel to serial shift registers. The only thing, though, is you have to have a way to tell when to start and stop. So just having 8 bits can be some problematic unless you're controlling the clock.
Right.
So,
actually,
and you mentioned.
I'm glad you brought that up. I've used LS 164s for driving LEDs, and now more recently, the favorite everyone uses is a 595. And the cool thing about the LS5 or HCT or whatever 595 chips, that it's just for those who don't know, it's a serial in, parallel out, dual clocked shift register with a carry output, so you can gang them up and they all share the clock, right? And data goes into the first one and then daisy chains through them all. So you can have an arbitrarily long shift register with as many outputs as you like. And this is why they're really a favorite for driving large LED displays and things like that. And they can go pretty quick too. Yeah, that's it. So so they're latched. That's what or registered. So you have that pin 14 there is the data input. Pin 11 is the shift clock. So on the rising edge on pin 11, whatever's on DS will be, pin 14 will be sampled into the shift register, and everything moves along 1 bit. And there's a master reset on that. And Q7S is the last bit to come through, can be daisy chained into the next chip. But then the storage register, STCP, pin 12, that's your storage clock. Now, somewhere, let me see if I can find this on the website.
or what I think of as a character clock sometimes. You have your bit clock, which does each bit, and then your character clock, or your STCP, says, okay, now I'm done, here's an entire 8-bit word. It's a word clock, is what I'm trying to say.
Yeah, I'm just trying to find this because...
I can see how you would do a bunch of, and I've driven LEDs from FPGAs and do something similar to this inside of FPGAs too.
I'm trying to find where this is. There's a, I want to grab a thumbnail of this. Okay, let's go open image, new tab. Maybe it's too small. Sorry for the delay. I should have been prepared.
Not a problem.
This is too small, but this is something I designed with those 595s. And I actually had the waveforms done out, and I realized this is SPI bus. Yeah, that's no good.
Ooh, yeah, it's
That's
real
fine.
small. Can you zoom in?
No,
Whoop, I'm back
it's
on
not high
Notepad.
enough. Not high enough resolution.
Okay.
Sorry about that. I printed out the waveforms. Maybe I can bring it up another day. But basically, you have to set and hold your next bit on the data line. Then you have a rising edge on the shift clock,
Right.
and you do that 8 times. You've got a whole byte. At the end of that 8 shift clocks, that goes high. But then your STCP clock has been low that whole time. It doesn't have to be low. It just needs one pulse of a rising edge to store the whole byte into the 3-state output register. And then your output enable can go low to drive the outputs and hold the outputs until the next byte is clocked in. So if you look at that, if you were to trace those waveforms out, it's SPI bus, basically. But
Right.
The problem is there's like 4 variations of SPI. There's CPOL 0, CPOL 1, or this has been documented in old Motorola data sheets from a long time ago, but there's like 4 different modes of clocking where you have a chip select, or you have your clock, your data, and what's the third one? It's chip select.
Clock data, chip select. Yeah.
Chip select goes low to say, hey, I'm addressing you, and then you get clock and data. And if you have a 595 hanging off that, chip select is connected to the store clock for the output register. So
Okay.
it goes low, nothing happens. The eight bits get shifted in, but then chip select goes high, and that forces that byte to get stored in. The problem is, in some hardware SPI implementations on some microcontrollers, the chip select, if you send multiple bytes back to back, the chip select just stays low.
Right.
And so
you have to generate on an edge driven.
So I designed a whole, multi-character 7-segment display that goes on top of an Arduino Uno R3, and use the software SPI and the hardware SPI. It worked great with an Arduino using an Atmega 328P, the R3 Arduino, no problem. Right. I plugged it into another Arduino clone that had an STM32 and hooked it all up, and the whole display was flickering and not displaying things right. And I realized it was its use of chip select and the clock timing with data was all different, even though they're both supposed to be SPI. So
were you using I/O ports to drive it? Because I/O ports have a fudge of almost a microsecond in there. They're not very logic driven sometimes. They're almost load driven. Their speed depends on the load.
Yeah, in both cases I was using, I think the Uno R3, I think the first implementation we were doing the bit-banged SPI, using the Uno library. By default, if you want to use whatever pins you feel like using for I/O, it has to use the software implementation.
Right.
And bit bang it. And that worked fine, but it's slow. And then it takes up CPU time. But then there's it did work with the hardware peripheral, which uses dedicated pins as well. We got that working no problem, and it was a lot faster. Not that it matters.
There's times when SPI is the first thing I get working, because it's like the thing that talks to everything. So it's kind of important. That's something I like about ESP32 microcontrollers is they have hardware SPI and they have hardware I2C, but you can assign them to any pins. Same with I2S, which is the other one. So I've used these kind of shift registers before to make delay locked loops, where depending on what tap you use and feed that back into your phase lock loop, of these taps, and in combination with the word clock and everything, I call it a dwell angle adjustment in the old days, but what it was a delay lock loop as opposed to a phase lock loop, which lines up two frequencies. What you do is, let's say, well, I want to lock to the third shift register bit. It'll move that output so that the third shift register bit's happening at the right time, but you can get the signal you want out of any one of these other ones.
Oh, that's cool.
So yeah. So when I didn't know the phase, I would usually go in with something like that and a selector between the outputs till if I need to empirically figure out what kind of delay I needed on something. And the problem I was fixing, the big problem I was fixing one time is we had a chip that didn't do synchronicity well. And it had it go metastable. We've been talking about that in the Discord channel. Well, here's a VLSI part going metastable, and I had to adjust its clock to a sweet spot. And then go beat up the designer, saying, I shouldn't have to do this, right? But we got it working, got it to the CS show, and then somebody sat him down and talked about how to synchronize an asynchronous clock.
That is cool. But there are parts, there are what we call primitives like this inside of FPGAs too.
There is.
If you're dealing with outside worlds and multiple clock domains, and you need to figure out a way of correctly sampling something or adjusting delays with things, sometimes there are IO resources in the actual FPGA chip that let you decide how many taps,
right, how many divides out, and they can be huge.
And there are DLLs, like I remember that too, like for also can be used like 1-bit digital versions of a PLL to adjust phase, but also clock frequencies. You can multiply and divide clock frequencies.
Right.
And so that's how you can put 150 megahertz crystal on the device, but inside you could have 4 different clock frequencies, and if you do it right, they can all be synchronized even so that they all fall on the same edge,
right?
At certain regular intervals. But
right,
yeah,
right. Because we still want some synchronicity. Whenever I design, I really detest asynchronicity unless it's a UART, and then in which case they make chips for that.
Yep. Copy this image. Let me copy and paste. Oh, I love it when they have a transparent background. Let's do it this way instead. This is, I wonder if I can zoom in on that. This is I2S. But really, the best, and this is from Wikipedia, so thank you, whoever uploaded
Wikipedia.
This.
Thank you, Wikipedia.
Yeah, so I2S is a little more complex. It stands for Integrated Circuit Sound Bus. So I don't know if you can see, I can't see the clock on the Skype call. You probably
yes,
can.
we see the serial clock, the word select, and the serial data for I2S.
Right. So word
different
select,
than I2C.
The problem is these have different names in different data sheets. Serial
yes.
clock is usually called bit clock or B clock. Word select is usually called LR clock, because what it means is left or right channel audio data. So each I2S stream is stereo.
I wondered where that LR stuff came from. Yeah. I never even stopped to think about it.
So when it's low, you've got the left channel audio. And that's just a basic serial data byte. A word. Word is, that's why it's called word clock as well. And so the receiving device, usually a microcontroller master device or DSP, is going to sample your data bits on a rising edge. And it's least significant byte, most significant byte.
Right. And you can see that the rising edge is dead center. It almost looks like you're using the right falling edge because of where those the horizontal vertical lines are. But the reality is it's sampled in the center of LSB and
Well,
in the center of MSB, right?
this is a really important point as well, and it also applies to anyone who's bit banging and writing
Yes.
code to make this,
Don't change two at once.
or designing a peripheral in either VHDL or Verilog to read and write I2S. Note that the rising edge is used by a receiver to sample the bit. So where you see right channel LSB, that's included because at the very beginning, when word select goes low, the point of showing that is that that's the least significant bit or byte or padding, because you may only have 16 bits of audio data, but you could have up to 32 bits of word, right?
Right.
Okay, so it may be a bit or it may just be padding after the last significant bit. So the most significant bit comes first, but what we're seeing there is when word select is high, we're reading the right channel audio data, and then it goes low, but it's one clock cycle later that we begin sampling the left channel data. And then same thing happens when word select goes high, there's one more clock cycle for the last bit of information for the left, and then we move to the right. So that's how that works.
There's a bit of pipelining in there. There's one pipeline stage.
But the point of both edges of the clock are important. The receiving device uses the rising edge to sample the bit.
Right.
So you've got good setup and hold times there, and you're right.
Yeah, the best setup and hold times. Yes.
And then the falling edge of the clock is used to generate or to clock out the bit from the transmitting device.
Right.
So
it's time for me to change. Yeah. And I'm 180 degrees out of phase from where you're sampling it, giving us the most setup and hold time, as opposed to people. I've known people that send the clock and the changes that the clock made down a cable, and they wonder why the clock can arrive a little bit early or a little bit late. And guess what? Metastability again.
Right. So
if you find you have to change the length of your cable and it looks like it works because you changed the length, or anything about, like, let's say you have 25 pins in a clock, and changing the cable you're not fixing it by changing the cable length. You're hiding the problem. The problem is you're using the same edge to generate the data as the receiver's clock, and there needs to be a clear setup and hold time. They can't happen right at the same time, because nothing happens identical, perfectly at the same time.
What this basically means is if you're using shift register logic to generate a stream, if you're using a parallel to serial shift register inside of an FPGA or CPLD to take parallel sample data from an A to D and then spit it out an I2S bus, you need to change your output bit on the falling edge. That's what that means. But the receiving device will use your rising edge, which should happen exactly half a bit time later, half a period later, and it may not if we could look at some different parts on an I2S bus on your fancy sampling scope there, we might see that they don't put the rising edge right in the middle of the bit time. Maybe it's closer to somewhere else, but it should be in the middle. And if you optimize your state machine to do that with shift registers, you'll be doing that.
The one thing I would add to that statement is usually setup time is more critical than hold, but not always. You can have a setup time of 20 nanoseconds, but a lot of LS parts, latches and stuff will need 20 nanosecond setup, but only 5 nanoseconds hold. So you can weight it a little bit, is my experience, but putting it dead center gives you the best of both, as you just stated.
Yeah, I'll see and there's variations on I2S that can be done with the same hardware, but are not exactly.
So why use an I2S data bus?
Well, I'm going to use it because I have audio codecs. So if you if you have an audio A to D or an audio D to A converter in a design, and a lot of products have now because you want or the case may be, you're developing a professional audio product.
Right.
You need a good means, and there used to be all sorts of proprietary buses for doing that. There used to be parallel. Back in the 80s,
Yes.
there was no I2S,
Yeah.
and it was even consumer and professional grade electronics equipment. In the mid 80s, they'd only just gone to 2-layer PCBs, so the signal
Right.
integrity wasn't there either, and it was really hard. So there were devices like the PCM. It was a company called Burr Brown that long since became part of Texas Instruments, but the Burr
Right.
Brown brand has been maintained for high-end audio. So they had all sorts of different buses and schemes for getting digitized audio into and out of chips. But the PCM, yeah, that's it. See if you can find a PCM 54 in there.
All right.
See if the PCM 54 is in there. So the PCM 54, I believe, used parallel. So it was quite a large, physically large chip in a ceramic package, used a lot of power. But it was the flagship audio converter of the day.
Yep, I got it. Hold on a second.
PCM 54. That book is all nice and white and has no yellowing. I'm surprised. It's like it's been on the shelf for years. Oh, the PCM.
It's not as old as me, but it's up there.
Yeah. So our PCM 53 and 54 were 16-bit DACs. So they used they're specifically for audio, but they use a parallel interface. And so you need a physically large package. But that was appropriate in 1990 because that was the only way of getting digital audio.
It was the only way,
around.
yeah.
You just had a lot of traces, and you had to manage signal integrity in very difficult ways. And yeah, so zoom into the block diagram of that thing. That's a beauty.
Yeah, it is.
So a DAC is a much simpler device, and they can almost work asynchronously. And one of the nice things that was actually used to effect in audio products in the 80s. I have, for example, rack delay units that use the PCM53 with 12-bit data paths and they have a compander to get the dynamic range, right, and the noise performance. You need compression before you digitize and expansion after you convert back to analog. But notice there's no clock pin on that thing. So
let me see if I can get go ahead.
The rate at which it converts a sample from digital to a digital word to an analog voltage is entirely dependent on the rate at which you latch and save each word of information into it. You have a latch in front of that. You send a word to it. It has a settling time. Then you have a sample and hold circuit after it that samples the analog voltage into a capacitor, and then that's buffered, and then a low-pass anti-aliasing filter. And so your sample rate is whatever you choose to throw bytes at this thing. There's no clock.
Right.
And so what it meant was there were devices that could have analog clock sources that were adjustable, and you could speed them up or slow them down to adjust delay times and things like that. And a lot of old guitar pedals work this way and have a very
kind of like resampling, only by gross quantization, by losing information.
And you could modulate the clock as well with another
another AC source. Yeah.
And so you could have a delay unit that was speeding up the delays and then slowing them down, and the pitch would go up and down with it.
I was going to say, it's frequency modulation, FM.
Yeah, it's like taking a tape and speeding up the motor or slowing it down. And that was the whole lot.
Which is the real way that started. They used to, I've seen like Pink Floyd talk about putting a thumb on the reel, right, to get that delay or that onset of delay.
Yes.
Yeah, right. So there was and when synchronizing vocals, then somebody would have to do that to do multi-tracking with vocals. You would have to somebody would have to sit there and make one of the magnetic tapes be lined up to the other magnetic tape, and they would do that by putting their thumb on it till it sounded good. That was
until Tom Scholz of Boston invented SMPTE. SMPTE.
Right.
Was using one of the analog tracks on the tape as a synchronization pulse. And so you could gang up multiple tape machines and they'd have a PLL and they'd all sync in together.
Right.
Brilliant.
So, and they still, SMPTE is still used today, and it's still an audio track, is my understanding. And I've even seen you can use your iPhone for a SMPTE controller just plugged into the audio output.
Yep, and even digital audio workstation software can send and receive SMPTE over Midi and other, can do time code in different things, so you can link other analog studio equipment into your digital workstation. So it's,
how strong are your Midi chops? Should we do a thing on Midi someday?
Yeah, we should. I'll show you something. Hang on.
To me, Midi's just some I/O ports.
And Midi's had some updates lately too. It's dusty in this room. This is a Midi foot controller I did using a Cypress PSOC 4.
Oh, I love the PSOCs. We've talked about them before.
Yeah, so this is just for controlling guitar equipment, and it's just a basic Midi output. But I'm working on a much bigger, more elaborate one that's going to have TFT panels all over it. But the Midi standards had some pretty good updates in recent years, and now there's faster versions and versions that can use smaller connectors and all sorts of stuff. So
I'm showing the date on my Burr Brown book. How many people here weren't even born in 1989?
Oh, that's a good question. Actually, and that reminds me, Bill, I haven't been keeping an eye on the chat. Is there who's talking on?
Chris just said a bunch of stuff here. Ever used a trick to offset audio to match timing for speaker at multiple distances? So what you're talking about is ambient delay. I assume he means through the shift registers, or?
No. Read the question again. I think it's about delay stacks of physical, the physics of the speed of sound, right?
Yes, that's what's underneath it. Is how do you make audio delays? Maybe in the old days, he might be asking too.
Yeah. So to do it analog,
digital. Yeah, we had analog and digital delay lines, but in the old days we had analog because we didn't have cheap digital audio.
And we couldn't get an A to D converter to go fast enough to get good quality
That's
audio
what I mean.
sampling.
Yep.
Until Burr Brown came along and solved the problem, right?
Do you remember the CCD based Bucket Brigade delay that Radio Shack sold? I tried to use that and was noisier than everything.
They're horrible. So, but they work the same way. So if you imagine, okay, so this is another subject we need to talk about: is sample and hold.
People are liking Midi, by the way.
Yeah. If you want to get good, if you want to delay or store a series of analog voltages, basically take an analog waveform, but you want to store it, you have to discretize it into a bunch of samples, right? Which are at fixed periods apart, and each one you have to basically get the average of the voltage during that sample time, or the midpoint.
Right.
And so the way you do that is you have a sample and hold circuit. All that is a
switch and an op-amp
and a capacitor and an op-amp that keeps the capacitor charged at its set voltage. So it's a very clever little circuit. And the switch, you have an analog input, and the switch connects the capacitor, and the capacitor, as immediately as it can, its voltage matches the analog input. So you need a very strong low impedance buffer for your input. And then the switch disconnects, but the capacitor maintains that voltage because it's charged now, and the op-amp keeps it charged at its fixed voltage through a feedback loop. So that's a sample and hold circuit. Then the other side of the sample and hold circuit, you have that voltage is kept more or less constant, and you have a bit of time, a brief sample period window, in which to compare that voltage with a comparator, an analog comparator, to the output of a D to A converter, which is just a resistor, R2R resistor ladder. So you adjust the numbers on the R2R resistor ladder until the comparator flips, and then you know what the value of that voltage is. So that's an A to D converter, and it's an A to D converter has a built-in comparator and a built-in D to A converter, the R2R ladder, all in one unit. So you can do A to D and D to A with one circuit if you plan it right. And Roland and Boss in their delay pedals used to do it exactly this way in their rack units. And I've got schematics for some of those. There's plenty of them available. You can find them on Google, but perhaps next time we can go over one of those and show the whole sample and hold process.
Right.
But
they are clever, as you said.
But the way it used to happen with the bucket brigades was it's just a long string of sample and hold circuits, one feeding into the next, and all sharing a clock for the sample. So you'd have this bucket brigade delay line, and you'd feed it maybe a 9 or 10 kilohertz clock, and so that's in the audible range. So you'd have to filter out your guitar signal to not include anything in that range. You have to anti-alias it.
Right.
And so we're just going to take the fundamental note basically and cut off everything above, say, 4 kilohertz. And we'll have a sample of 9 kilohertz, and that gives us maybe, I don't know, 300, 400 milliseconds of delay time through this bucket brigade. So that it's called a bucket brigade because you're taking these samples and you're passing them from one
charges.
One
you
sample,
pass like the charge on a cap,
yes,
on the gate of a FET, and you try and pick it up and drop it at the gate of another FET. The problem is not all the charge makes it there, and that difference in charge is noise.
Yeah,
yes.
They're lossy and they're very noisy.
And sometimes it can be greater than, sometimes it can be less than. It's just and you get to the end of the brigade, and it's the accumulation of all the noise of all 256 stages is my memory.
So a digital delay line does exactly the same thing, but instead of using that analog bucket brigade, you just sample all of your data coming in, and you have a buffer of memory, and you set it up like a circle. So when you get to the end of the buffer, you go back to the beginning. In your microcontroller code or in your FPGA design, whatever you're doing, you have pointers. You have a read pointer and a write pointer, and if you want 400 milliseconds delay or thereabouts, you go that many samples apart, 400 milliseconds in memory, and this one's writing and this one's reading behind it, and when this one gets to the end, it goes back to the beginning, and this one gets to the end, it goes back to the beginning, and it forms a circular buffer. And you get
reverb out of that, some reverb effects and things like that.
Reverb, echo, even chorus.
Echo. That's
they're all based on having a circular buffer delay line that operates in that way.
Plus, you can, if you modulate the clock of the brigade line, then you can make some cool whooshing effects and things.
You can speed it up and slow it down, and that's harder to do in a microcontroller in software because you have fixed sample rates and you can't change it.
Right. If you make it shorter, where does the extra go? Yeah.
So the only way is you have to have a fractional sample, and so you have to have an algorithm that interpolates between two samples at the point that you want your theoretical sample to be coming from, and that you can only vary up and minus, forward and back up to 2 times the sample rate or half the sample rate.
That's a real important point, because what we do easily in analog, we modulate that clock that these analog charges are getting brigaded by. But in digital, we got rules that deal with the sample time and how do we, translate the different samples into something that's still valuable when we're done. If 48K to 40K, for example.
And that's where the secret sauce is in expensive
upverting
audio,
and stuff too.
Very expensive audio plugins and effects units. That's kind of some of their secret sauce is the research they do into how do we do this kind of thing without adding noise or making poor signal quality.
Right.
So,
hey, I have to run. It is. We are up at 3 o'clock here, and I have to go get a vaccination. Yay! Get vaccinated.
Build the guinea pig.
Yeah, we talked about that. I was in the I'll tell you stories about swine flu shots being in the service. It was fun watching people fall over. And we had a saying, you could tell if they really passed out or not by where they hit their head when they fell over. Drill sergeant would walk up, he'd go, he hit his head? No, get him up. You know, pool of blood. Oh, he's not faking it. Yeah, he really fell out.
Wow.
So
cool, man.
Hey,
good talking to you
yeah,
again.
Mate. Good seeing you. We won't see you next week, but we'll figure out something for next week. And then we're working on, I don't want to say a surprise guest for the week after, but I'm working on getting somebody that I think everybody would enjoy. He just has to say yes. So
yeah, hopefully.
Yeah. So thank you, everybody. This was a blast. We tore the heck out of I2C and didn't talk about JTAG, or Midi for next time also. We got some things to talk about.
We'll come back around to JTAG once I've done more work on my FPGA
there you go.
ESP board. We'll have more to talk about.